Section 4.2 is on page 174, talks about homogeneous with constant coefficients. This is a repetition of what we did in chapter 3, but now we're going to go for a higher order. To do that, I need to review with you a bit of trigonometry. I already uploaded complex numbers in the Canvas files. You could look them up. So, in each problem 1 through 4, express the complex number. So you're going to go from complex to polar, or rectangular to polar. The key is always plotting the point. You want to figure out where this point is. This is at -1 radical 3. And we know how this goes. R is simple to find using Pythagorean. You could say R squared is radical 3 squared plus a -1 squared, which is 3 plus 1, 4, and R equal plus or minus, but in complex, let's keep it positive. You know what, let me use capital letter just like they do. And I need the angle, so here you're going to take tan of theta to equal, and you're going to find the reference angle, radical 3 over 1. You ignore the plus or minus. So my reference angle for this problem in quadrant 1 is pi over 3. And now you're going to say, well, what is this angle? That's really 2 pi over 3 in the second quadrant. You're going to say this is, instead of you saying this is 2 into the cosine of pi over 2 pi over 3 plus I, the sine of 2 pi over 3, it's going to be much simpler for us to use Euler's formula, which is twice e to the 2 pi over 3I. And if you weren't taught Euler, I taught Euler in my class, but if you weren't taught Euler, you were taught De Moivre's theorem, and I could say that's e to the 2 pi over 3 plus 2 pi k I, because every time I add 2 pi, I'm back where I started. Another example that comes up later on, I want to give you another problem. There are only 2 examples in the book. I really want to tackle this problem. -3i, that's 1, 2, 3, you're right there. So you rotate to 3 pi over 4 over 2, and you say -3i is the equivalent of r, which is 3, that many units, e to the 3 pi over 2i, but we're going to need 2 pi k I because we want to find multiple solutions. Now I'm going to run down and start the problems, and notice the wording. That's really a good hint. I want to look at problem number 6. Problem number 6, we start with, forget example 4, determine the indicated roots of the given complex number. So I need to take 1 plus I and figure out what that is. 1 plus I, you move 1 unit to the right and 1 unit down. 1, -1 basically, right? So R is right there. That's simple. That's radical 2. And the reference angle, tan of theta, equals 1 over 1. You ignore the minus, so the reference angle is pi over 4. And in this quadrant, that would be 7 pi over 4. So I could say this is radical 2 e to the 7 pi over 4 plus 2 pi k I. And since they're raising that to the 1/2, I'm going to raise that to the 1/2. And notice that radical 2 is actually 2 to the 1/2. So if you raise that to the 1/2, that is 2 to the 1/4, which is 1/4 radical 2e, and if you multiply those, that's 7 pi over 8 plus pi k I. This will be the general solution, something we're going to need in the coming chapters, right? And if I work that out, I could get as many zeros as needed. In this case, I'm going to need 2 of them because I'm taking square root, meaning I must have had z squared equal 1 minus I, so I need two solutions. First solution, you let k equal 0. You will get the fourth root of 2 e to the 7 pi over 8I. That's fine as an answer. And I'm gonna let k equal 1. I will get the fourth root of 2e. If I take pi plus 7 pi over 8, that's 8 plus 7, 15 pi over 8I. And what happens if you proceed and go to k equal 2? Well, you're going to start repeating. You can't get more than 2 if you did a 1/2. You could do the same work and get 3, make that a 1/3, 4, 1/4, and so on and so forth. If you add 2 pi to that, you end up with 2 pi plus 7 pi over 8, which is the equivalent of, let me see, 7, 8, 23 pi over 8I. And we know that's the same as if you take away 2 pi, you just started repeating. So no need to do that. You can only get as many solutions as you set the problem to find. And next problem up, we're going to tackle number 8. And let's look at this. Hey, this is a homogeneous, it equal to 0. It is a linear equation with constant coefficients. What does that mean? We're going to let y equal e to the rt. In this case, I need 3 derivatives. R e to the rt, y double prime is r squared e to the rt, and y triple prime equals r cubed e to the rt. This will be r cubed e to the rt minus r squared e to the rt minus r e to the rt plus e to the rt equaling 0. You factor out e to the rt and you get r cubed minus r squared minus r plus 1. Some of those you could factor. You're going to have to use factoring of polynomial. Another section that I uploaded for you in Canvas. You could look those up. I'm going to review that with you as well. E to the rt cannot equal 0. It must be that r squared, I'm going to factor those by grouping into r minus 1 minus r minus 1. R minus 1 is common in both. You'll have r squared minus 1 equals 0. So I have r minus 1, and r plus 1 equals 0. So I'm getting r to be 1 or negative 1. I get e to the t, e to the t, e to the negative t. And remember to make those linearly independent. Since this has multiplicity 2, I multiply that by t. And the general solution is y equal c1 e to the t plus c2 times t e to the t plus c sub 3 e to the negative t. And there it is. That would be my general solution for this problem. And here's a review from Algebra. Rational zero theorem. If you're given a polynomial, right, the degree is higher than 1 with constant coefficients, and those are integers. If they're not integers, you factor out the fraction, make them integers. That doesn't come up for us. If you take the leading coefficient and take the factors of that, the constant, divided by the factors of the leading coefficients, those would be the possible rational zeros of f of x. Again, you did this back in the days when you graphed polynomials. I could go over that with you, review it a bit if you like in the discussion. So I'm looking at this problem. This is a 6-degree polynomial. It is linear with constant coefficients. I'm gonna let y equal e to the rt, and you know the drill. This is gonna be r to the 6 e to the rt minus 3r to the 4th e to the rt plus 3r squared e to the rt minus e to the rt equals 0. Factor e to the rt out. You will have r to the 6 minus 3r to the 4th plus 3r squared minus 1 equals 0. E to the rt can never equal 0. It must be that r to the 6 minus 3r to the 4th plus 3r squared minus 1 equal to 0. Factoring here could work. No, it doesn't work. Factoring doesn't work. So, but what's the good news? If I take the constant, which is 1, the leading is 1, the only possible rational zeros for this problem, the only possible rational zeros would be plus or minus 1. That's it. So let's see. Does 1 work? If I look at this, if I put 1 in there, that seems to work because I'm looking at 1 minus 3 plus 3 minus 1, that's a 0. So remember syntactic division, r to the 6, r to the 5th, r to the 4, r cubed, r squared, r, and the constant. And what I want to do, I want to factor this. 1 multiply 1 multiply. That works. You go for 1 again. See if that works. And that does work. 1, 2, 3, 4 minus 4, that's a 0. And you try 1 again. 2, yep, that works again. Today's my lucky day. And here, I could factor the rest. So I could say the rest now is really, actually, 1 doesn't work anymore because they're all positive. I could try negative 1, see if that works. That'll save me some work. 1, okay. One, negative 1, 2, negative 2, 1, negative 1, and a 0. And I'm left with r squared plus 2r plus 1 equals 0. That's r plus 1 squared equaling to 0. So basically, maybe I should have, let me get this. Squish that here. Maybe I should have did that right there. And I should have did that here. R squared plus 2r plus 1 equals 0. R plus 1 squared equals 0. So if I look at this, this is actually r minus 1, 1, 2, 3 of those, and r plus 1, 2, 3 of those equals 0. So from this, I know that I have e to the t, e to the t, e to the t, 3 of those, and e to the negative t, e to the negative t, e to the negative t, as my fundamental set, except those are linearly dependent. How do I make them linearly independent? Multiply this by t, multiply this by t squared, multiply this by t, and multiply this by t squared. And the general solution is y equal c1 e to the t plus c sub 2t squared e to the t plus, I'm getting ahead of myself, plus c sub 3 t squared e to the t plus c sub 4 e to the negative t plus c sub 5 t e to the negative t plus c sub 6 t squared e to the negative t. And that would be my homogeneous general equation. The fun part, of course, is not really listing the answer. The fun part is actually finding those C's, C1, C2, C3, all the way to T. Next problem up, number 16, the same deal. That is a linear equation with constant coefficients. That means y equal e to the rt will work. And here we go. If I let y equal e to the rt, I'm getting e to the rt times r to the 4th plus 2r squared plus 1 equals 0. E to the rt, of course, can never equal 0. It has to be r to the 4th plus 2r squared plus 1 equals 0. This does factor. So I'm getting r equal plus or minus I multiplicity 2. And the fundamental set is the cosine of t, sine of t, cosine of t times t, because they're repeating, and sine of t times t. And the general solution is y equals c sub 1, the cosine of t, plus c sub 2, the sine of t, plus c sub 3t, the cosine of t, plus c sub 4t, the sine of t. And that would be my general solution again. I'm going to continue this in the next video.